In this video, we're going to talk about continuity. The idea of continuity can be thought of informally as the idea of being able to draw a graph without lifting one's pencil. So three types of discontinuity are shown below. You can have a hole, you can have a jump discontinuity, you can have a vertical asymptote, and there are other examples as well. But there's a more formal definition than just saying, well, it's something you can draw without lifting your pencil. Specifically, we say this. A function is continuous at x equals a if f of a exists and if f of a is equal to the limit as x goes to a of f of x. So let's graph the function shown, determine f at -1, determine the limit as x goes to -1 of f of x, and then see if f is continuous at x equals -1. And from the definition a moment ago, we'll see that if the value here exists, and if the value here exists, and if they agree with each other, then we'll be able to say yes, f is continuous there. Okay? So we graph the curve, okay, and we want to determine, so we graph that function in part A. Now in part B, we want to evaluate f at -1, and technically it's important that we plug it in the appropriate side of in the appropriate function. X equaling -1 belongs to x squared minus 3 because that's where x is less than or equal to -1. So -1 is part of that domain, so we're going to plug it into the x squared minus 3 part. Okay, so that means f at -1 is simply -1 quantity squared minus 3, which is -2. All right, cool. We've answered part A, we've answered part B. Now let's answer part C. Let's figure out the limit as x goes to -1 of f of x. Well, as x goes to -1 from the left, as shown by that red arrow, we see our y-coordinates getting infinitely close to -2. And as x goes to -1 from the right, as shown by that red arrow, we see that the y-coordinates getting infinitely close to -2. So those limits are shown and they agree with each other. And so in part D, since f at -1 exists and the limit as x goes to -1 of f of x exists and they agree with each other, they equal each other, therefore we can say the function is continuous at x equals -1. Intuitively, we knew that because we see we can draw that without lifting our pencil, but still, those are the steps you have to show. So let's determine if that function shown is continuous at x equals 2. Well, we don't specifically have to draw the curve, but in this case we've drawn it. And we now can say as x goes to -2 from the left, y is getting infinitely close to 6. Now, how do we know that? Well, we know it because this is a continuous function, and it sounds weird for me to give the answer within my solution, but we know all polynomial functions are continuous, so we can say that the value, we can literally plug in an x value of 2 and see what the y coordinate should be. So 2 cubed minus 2 actually equals 6. So we know the point 2, 6 is going to be on that curve. So we plot it. There's 2, 6. And so we then determine the limit as x goes to 2 from the left, which was shown there to be 6. And we determine the limit as x goes to 2 from the right, which is shown here to be 6 using a graphing approach. And so we can say the limit as x goes to 2 of f of x equals 6. But we also know that f of 2 equals 6. And since f of 2 equals the limit as x goes to 2 of f of x, therefore f is continuous at x equals 2. Now let's see if this function here is continuous at x equals 2. Well, f at 2 actually doesn't exist. Now, the limit as x goes to 2 of f of x might very well exist, but f at 2 itself doesn't exist because when you plug a 2 in, we get an indeterminate form. We get 0 over 0. It's undefined. So the function So f of 2 doesn't exist, so the function can't possibly be continuous at x equals 2. But now let's change it up just a little bit, and let's say, okay, we acknowledge x squared minus x minus 2 over x minus 2 is not defined at x equals 2, but let's make it a piecewise function where everywhere other than x equals 2, y will be given by that expression, but at x equals 2, y will be given by the value 3. Now we have something that actually is defined at x equals 2, so that's cool. So what we do is we do a little bit of factoring, and we see that x minus 2 over x minus 2, they can each cancel. And so what we really have is this expression here, x squared minus x minus 2, is just like saying x plus 1. And with the restriction of x can't equal 2, but we actually have that restriction here, so that's awesome. So really what they're asking us about is the function f of x equals x plus 1, where x doesn't equal 2, and 3 when x does equal 2. Okay, so cool. So we can draw in the first part of that, the x squared minus x minus 2 over x minus 2, as mentioned earlier, is the same as x plus 1, but x can't equal 2. So we draw the line y equals x plus 1 with a hole at x equals 2. But then we say, okay, but we also have to plug in the point 2, 3, because when x is 2, y is 3. Well, coincidentally, the point 2, 3 actually fills in the hole. You can see I just filled it in red. Okay? So that's what's shown there. So now what we're going to do is we're going to, we can see that the limit as x goes to 2 from the left of f of x is equal to 3. The limit as x goes to 2 from the right of f of x is also equal to 3. But x, so that means the limit as x goes to 2 of f of x exists and is in fact equal to 3. And also f of 2 equals 3 as stated earlier. So that means, as stated right here in fact, so that means f of 2 equals the limit as x goes to 2 of f of x, so the function must be continuous at x equals 2. Now, we're going to determine whether the function shown is continuous at x equals 1. Well, when we draw that piecewise function, we get this right here. So we can see that f at 1 equals 3 because an x value of 1 is coming out of that domain, so the y coordinate must be 3. So that means f at 1 is 3. Cool. And then f at 1 exists, but now we want to determine if the limit as x goes to 1 of f of x exists. So we approach it from the left-hand side as shown by that red arrow. The limit as x goes to 1 from the left of f of x is equal to 4. And now as shown by that red arrow, the limit as x goes to 1 from the right of f of x is equal to 3. That means the limit as x goes to 1 of f of x doesn't exist. So f of 1 exists, but the limit as x goes to 1 of f of x doesn't exist. That means f is not continuous at x equals 1. We have our answer. So general observations regarding continuity. A function that's not continuous has some type of break in its graph. It could be a hole, jump, vertical asymptote. All polynomial functions are continuous for all real numbers. So one of our earlier questions, it was just a straightforward polynomial function. So something you can now remember is that all polynomial functions are continuous for all real numbers. We actually mentioned that briefly in, well, not briefly, we mentioned it in advanced functions. Now, a rational function h of x equals f of x over g of x is continuous at x equals a if g of a doesn't equal 0. In other words, if the denominator is not 0, the fraction exists. Now, a rational function in simplified form has a discontinuity at the zeros of the denominator after you've simplified it. Because those will be vertical asymptotes, and vertical asymptotes are discontinuous. But before you've simplified it, they might be holes. So you have to be able to simplify it before you can say what's stated in number 4. And finally, when the one-sided limits are not equal to each other, then the limit doesn't exist, and the function is therefore not continuous at that x value. So finally, let's determine the value of k such that the function shown is continuous over all x element of the reals. Now the function 3 minus kx is continuous over all x element of the reals, and the expression x squared is continuous over all x element of the reals. So the only possibility is maybe there's a discontinuity at x equals 4 because there's some sort of a jump because we have a piecewise function. And that kind of makes sense to us because a lot of times when you graph a piecewise function, one function looks like this and the other function might look like that. And there's a gap here, and that gap is creating a discontinuity. But intuitively, we might understand if we can just get that closed circle to fall right on top of that open circle. In other words, if the y-coordinate of the closed circle equals the y-coordinate of the open circle, then there will be a continuity, not a discontinuity. So what we're going to do is we're going to say if we let x equal 4 in the top expression, we'll get a y value, and that x and y value will indicate where there's an open circle on the graph. Okay? But if we let x equal 4 in the bottom expression, we'll also get a y value, and that'll indicate where there's a closed circle on the graph. And if the open circle and closed circle are at the same point, we know there's no discontinuity and the curve will be continuous. So what we're saying is this. If we have an open circle and then a closed circle, and they don't have the same y coordinate, but they do have the same x coordinate, then we're discontinuous. But if we have an open circle and then we also have a closed circle right on top of the open circle, well, now that function is continuous because we don't have to actually lift our pencil off the paper intuitively. So we know the open circle and the closed circle are both at an x value of 4. We just need to now see what the y values are and set them equal and solve for k. So at x equals 4, 3 minus kx is the same as 3 minus k times 4, which is 3 minus 4k. So in other words, we have an open circle at the point 4, 3 minus 4k. Now, at x equals 4, this bottom part, where x is greater than or equal to 4, and therefore gives us a closed circle, that bottom part is equal to 16. So we've got a closed circle at 4, 16. So our x-coordinate, we want these two to fall on top of each other. Our x-coordinates are the same, but now we need our y-coordinates the same. We need 3 minus 4k to equal 16. Well, that's a pretty easy question at that point. Just set 3 minus 4k equal to 16. That means negative 4k equals 13, and so k is negative 13 over 4. And we've answered the question. If k is negative 13 over 4, then we have a continuous function.